So section 2.1 is discrete random variables. So first of all, we define a random variable as something that assigns numerical values to outcomes of a study or experiment. So for example, let's say we want to keep track of the number of radios sold in 1 week. We'll let x be a random variable that represents the number of radios sold. So our possible outcomes is we could sell 0 radios, 1 radio, or 2 radios, and etc. You could probably keep going past 2. So our random variables would be 0, 1, or 2. Now before your experiment is carried out, your outcome is uncertain. And that's the very important thing about all of our probability, is before something happens, you don't know what the actual value of your random variable will be, which is why we have probability as something uncertain. So before we actually spend the week selling radios, this x, which is the number of radios sold, is uncertain. We don't know what it will be. Now, there's other ways you can assign numbers, even if something didn't seem very numeric. So for example, let's say I conduct a survey, or an experiment, if you will, to see if any students have taken a statistics class before, and their answers come in the form of true or false. A random variable has to assign numerical values, so I can just decide, I'll say false, I'll put a 0, and if it's true, I'll put a 1. Now, I just decided on that. I could have switched those two numbers, or really even picked other numbers. That's just binary is common of 0 and 1. So let's look at this next one. Consider tossing a coin 3 times and observing whether we get heads or tails. Our sample space of all of the possible outcomes would be head, 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 tail, head, tail, head, head, tail, tail, etc. And we find that, you could find that by drawing out a tree to make sure you don't miss any. And we'll let the random variable x be our number of heads. So we can actually go ahead and toss the coin 3 times. I always forget that I actually plan to do this. I think last year I had to borrow a coin from someone. Okay, so I'm tossing the coin currently as we're talking, so I just got a tail, a head, and a tail. So for that one specific trial, what is my value of x? X is the number of heads, so my value of x would be 1. I only got 1 head. Now if I was to try it again, I should get something different. I got tail, head, and head. So for this specific trial, what would be my value of x? This time I got 2 heads, so x would be 2. Now a lot of this class is just keeping track of all of your symbols and making sure you're using the right one. So we will use the uppercase letters x, y, z to represent our actual random variables. And when you have a big X, that kind of means this is a random variable. I don't know what the value will be. We use lowercase letters to represent the values actually taken by the random variable. So like little x equals 1, little x equals 0.3, etc. So up here, this would be little x equals 2. And I always have to do a kind of curved little x so I can keep them straight. Or little x equals 1. Now, in general, we'll say the probability that x equals x, so you always do your big capital case as your unknown. And then the little x represents your specific number. So if you want to find the specific probability that little x is 6, we would write the probability that big X equals 6. So the next thing you have to know how to do is find a probability distribution. And that's some way to describe the values of x and their probabilities. We could show this with formulas, tables, graphs. There's lots of different ways to show it. So first let's look at some theory. If we were to toss a fair coin 3 times. So here again are all of my possible sample space outcomes, head, 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 tail. What would be the probability of each one of these outcomes? Okay, so we'll go ahead and wait for someone to give us an answer here. What should these probabilities be? let's see, we have their sound turned on, right? Okay, so I'll wait. What are the probabilities and why? Okay, because okay, there are 8 outcomes and they should all be equally likely, right? So they're all 1/8. Okay, so now on each one of these, go through and say, well, what would my actual random variable xi be? So once again, let's remember that x is getting heads. Okay, so, or x is specifically the number of heads. So in my first one, little x equals 3. My next one, head, head, tail, that would be little x equals 2. Let's go through and fill them all out. So I have a 2, a 1, a 2, 1, 1, and 0. Okay? So we're just counting the number of heads in each one. So when we go through it and we fill out this nice little probability distribution, going through, I say, okay, what are my possible values of x? X, I could have a 0, I could have a 1, I could have a 2, or I could have a 3. Those are my different values. Let's see, if I wanted to get 0 heads, the only way to get that is if I had tail, tail, tail. And the probability of tail, tail, tail is 1/8. But now if I wanted to get 1 head, how can you get 1 head? I could get a 1, or a 1. Now notice I am saying ors here, so we should be adding probabilities. So this one was like head, or tail, tail, head, tail, head, tail, head, tail, tail. Those are all options that give me 1 head. And so I'd have 1/8 plus 1/8 plus 1/8, or 3/8. So getting 1 head is more likely than getting 0 heads. For the 2, again, you go through and you do the same thing. You say, okay, well, how can I get a 2? A 2, 2, 2. There were 3 different ways. So 1/8 plus 1/8 plus 1/8 would once again be 3/8. And to get 3 heads, the only way to get 3 heads is head, head, head. So that would just be 1/8. And this would actually be a full probability distribution. If you write out a table like this, you have each value of x and each probability. That counts as your probability distribution. So we have random variables, and then there's different types of random variables. So you have discrete random variables, and this is going to be any variable x that has a countable number of possible values. So this means you could count or list all the possible values of x. And we'll look at some examples if that didn't sink in yet. And you have a probability mass function, which we call a PMF, which is the set of all the probability values, pi, assigned to each x value for the random variable for discrete random variables. So discrete random variables have a PMF. So that means this little thing right here, it had each value of x and it had each probability. This is a PMF, or a probability mass function. It just tells you each value of x and each probability. Now all probabilities must satisfy 2 requirements if you're going to have a probability mass function. Every probability must be between 0 and 1, and all of your probabilities have to add up to 1. That shouldn't be surprising. We've already said that once before. And some more specific notation. We write the probability that our random variable x takes the value xi, and that probability is pi, as the probability that x equals some specific number is a specific probability. So here's the PMF for the number of heads if we toss the fair coin 3 times. I just rewrote this down here. Is this a valid probability distribution? So first, as you look at it, you'll notice here I say xi, pi. Those are notations. And I can tell you, so this is the probability that x equals 0. So it's capital X equals 0 is equal to 1/8. So the specific x value is 0, the specific probability is 1/8. Or the probability that x equals 1 is 3/8. So that's what it actually looks like, etc. in your actual notation. Then we want to check, is each probability between 0 and 1? Okay, we have 1/8, 3/8, 3/8, 1/8. That seems correct. Then you want to add them all up and make sure they add up to 1. So 1/8 plus 3/8 plus 3/8 plus 1/8. And that gives us 1. So we met both things. So this would be a valid probability distribution. Or a valid PMF. Let's look at another one. So Sean thinks that he can model the probability of having X accidents in his factory by this formula. So probability that X equals a specific value is going to be 1 over 2 to the power of X plus 1. And X can be 0, 1, 2, all the way up to possibly infinity. And we want to know, is this a valid probability distribution? So I've shown you kind of here what this looks like. So if X equals 0, if you plug 0 into that formula, you get 1/2. For 1, you get 1/4, 2, you get 1/8, 3, you get 1/16, etc. So you can keep going down. You can also see I've graphed it here. So 0 is at 1/2, 1 is at 1/4, etc. So this is what it looks like. So to check if it's a valid probability distribution, you want to see, is each probability between 0 and 1? Well, for any X value we plug in, we're going to be 1 divided by 2 to some power. That's going to be small numbers. That's going to be less than 1. We shouldn't be getting any negatives, so we should be between 0 and 1. Then we want to see, if we added them all up, would we get to 1? So how do you represent that you're going to add them all up? That's when you have to bring in your sum. Because I'm going all the way up to infinity, I can't actually add them all up in my calculator to make sure they add up to 1. So we want to do the sum from 1 over 2x plus 1. And we have to start at 0 because my smallest one was 0. And we're going to have to go to infinity because they didn't give us an upper limit. Now in this class, we assume that you guys remember everything from your calculus classes. And you can remember that if you have the sum of r to the power of n, it's going to be 1 over 1 minus r, as long as the absolute value of r is less than 1. So what we'll do is we'll come back and we'll rearrange this just a little bit. And we'll say this is the same thing as 1/2 to the power of x plus 1. So we kind of look like this r to the power of n, but not quite. What I could do is this 1/2 x plus 1, I could split that up and I could say this is the sum of 1/2 to the x times 1/2, and I could pull out that 1/2. So we'd have 1/2, the sum from x equals 0 to infinity, of 1/2 to the power of x. And now I can use that formula. So this seems pretty similar. R is going to be 1/2. And instead of n, we just have an x. So this is going to be 1/2 times r, 1 over 1 minus r, which is 1/2. And so this is 1/2 times 2, which equals 1. So it does all add up to 1, so check, and this would be a valid PMF. Now, I understand that you probably don't remember all of your tricks from your summations, and that's okay. I don't actually expect you to in this class. That's not the focus of this class. Instead, if you wanted to do something like that, I suggest you use either your calculator, or if you don't have a calculator that can, go to the site that's called wolframalpha.com. And this is actually very useful for everything in this class. If you're doing integrals and you don't remember how to do integrals, it would be very useful. If you're doing derivatives and you don't remember how, you can come and do it all on here. So we could say we just want to do the sum of 1 over, let's see, 2 to the power of x plus 1 from x equals 0 to infinity. Usually it's pretty good at guessing what you want, You don't have to have super technical notation. Just check, is that what I asked it to do? Sum x equals 0, infinity 1 over 2x plus 1, and it gives me 1. So again, you can do almost all of your calculus here on Wolfram Alpha. As far as exams, I'll only ask you to do very basic calculus on exams. So basically just the normal power rule. But for your homework, you'll have to do more complex calculus. You can do it in your calculator or you can do it here. So let's pause here. Do you have any questions? Oh, how is R 1/2? So this is just saying, I was trying to make it match up to my formula. It has an n here, whereas I had an x, but we have x, and then it just has r to what power? And so I just have 1/2 to a power, so I said r is 1/2. But again, that's more of the actual calculus thing, assuming that you remember that, but I realize you probably actually don't. Statistically, all you have to remember is you have to check to see that they add up to 1. So let's try another example. Let's now say we have a quiz with 3 questions, and let's assume that the student has studied enough that they actually have a 0.8 probability of answering each question correctly. And let's let x be the number of correct answers, and x is a random variable. So let's just say here the probability of getting one right, it told me is 0.8. And then what is the probability of getting one wrong? 0.2, because they always have to add up to 1. So what we're going to do to find an actual probability distribution is you go through and you list out all of your possible outcomes. So you could have right, 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 wrong, wrong, right, etc. And you have to find the probability of each one, because these aren't all going to be 1/8 because they're not all equally likely. So let's see, probability of individual outcome. So if I want a right, 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 I do the probability of right times the probability of right times probability of right. Excuse me. And so that would be 0.8 times 0.8 times 0.8, which is 0.512. Or if you want a right, right, wrong, the right is 0.8, the right is 0.8, and the wrong is 0.2. So this is 0.128. And for right, wrong, right, we'd have 0.8, 0.2, and 0.8, which once again is 0.128. Now to save time for the rest of them, I've gone ahead and wrote out what all of those probabilities would be. And once you find every possible sample space outcome, you find the probability of each one, and then you go through and write down the value of x. So in this case, how many rights do I have? Remember, x is the number of rights, so x would be 3. And for right, right, wrong, x would be 2. And 2, so go ahead and fill these out. Just count the number of rights on each one. And as you went through, you should be getting numbers ranging from 0 to 3. So in my next table, I have a place for you to put each x value and each probability. So my x's range from 0 to 3. So if I want to get a 0, what's the only way you can get a 0? Or there's only one way you can get a 0 here, and that probability is 0.008. For a 1, how many different ways can I get a 1? Let's see. I have a 1, and a 1. Okay, or 3 different ways to do it. And it looks like they're all 0.032. So 0.096. And for the 2, looks like I have a 2, a 2, and a 2, and they're all 0.128. So 0.128 plus 0.128 plus 0.128 gives me 0.384. And finally, the only way to get a 3 is right, and that's 0.512. So this, it has each specific x value and each probability, so that would be my PMF. You'll also usually want to graph your PMF. And so down here, you'll put x along the x-axis. So you'll put each x value. And on the y-axis, you put your probability. And then you have to come up with some logical scale. It doesn't really matter. You can pick different things. I'm going to do 0.1, 0.2, 0.3. And then we graph each probability. So for 0, my probability is 0.008. That's actually really, really small. And at 1, my probability is 0.096. At 2, my probability is 0.384. And at 3, my probability is 0.512. Now, if you think about this, do I have any chance of getting an x of like 1/2 or an x of 1.7? No, right? You're not getting 1.7 answers correct. It's only 0 or 1 or 2 or 3. Those are my only possible values. And so the way we represent this is we'll draw a little line going straight up. And we don't have anything in between, and that represents the fact that you can only be 0 or 1 or 2 or 3. Let's make a little note of that. You can only be, let's make this bigger again, 0 or 1 or 2 or 3. Now, because you have only those specific values you can be, that kind of clues you in that it is a discrete random variable. So discrete random variables are always you can only be this or this or this. You have a set values that you can possibly be. Let's try one more, and then we'll pause for some questions if you have them. Let's say I want to roll 2 6-sided dice and find the sum of the numbers. We'll let x be the random variable representing the sum of the number on the 2 dice. So I made a little table here just because it's one way for me to organize it. I said, okay, if I get a 1, 2, 3, whatever I get on die 1, I'll put at the top. Whatever I get on die 2, I'll put on the side. And in the middle, I put the actual sum. So 1 plus 1 is 2, 2 plus 1 is 3, 3 plus 1 is 4, etc. So on the inside are my actual sums. So the actual sums are on the inside. This isn't a statistical thing of you have to know you make a little table like this. This is just I have to have some way to list out all of the possible outcomes. This is how I did it. So as you look at that table, what are my possible values of x? My sums can start at 2, and it looks like they go all the way up to 12. So let's write that in. And looking at this, it does seem like I can only be a 2 or a 3 or a 4. I have very specific values I can be, so this would be a discrete function. Now we need to find the probability of each one. So to do this, you go through and you say, okay, I want to get a 2. How can I get a 2? The only way I can get a 2 is this 2 right here. So that is one way to get a 2. And how many total possibilities are there? There are 36. So what I want you to do is go ahead and take 2 minutes and see if you can fill in this probability chart and graph it by yourself, and I'll work on it up here. We can check our answers at 2 minutes. And let's see what we got here. So in my probabilities, I went from 1 out of 36, and each one seemed to get higher up to the 7 at 6 out of 36, and then I went back down. So when I graphed it, you could have picked any scale you want on the y-axis. I just did 1 out of 36 as my scale, so I didn't have to convert them to decimals. So my graph looks something like this. There are a few things you might notice about this graph, like it seems symmetric, right? You can fold it in half and it's the same on both sides. And also, I like graphs because you can look at the graphs and tell me what seems the most likely. Which one has the highest probability? A 7. So that's why if you play any games where you roll 2 dice and add them up, 7 is the most likely number. Whereas a 2 and 12 aren't very likely at all. And right here, this table we have up here, that's what you would actually, again, call your PMF. So your PMF is just some way to list all of your x's and all of your probabilities. So now we'll actually go through and make it more interesting, and we'll find some probabilities based on what we wrote down. So let's find the probability that x is greater than or equal to 10. Now, anytime you do this, you should always be writing out, well, what are the things that satisfy that? What outcomes actually give me an x greater than or equal to 10? So to get x greater than or equal to 10, I would have to have x equals 10, or x equals 11, or x equals 12. Now, as you do all probability problems, you have to decide, think to yourself, should this be an or an and? Now, to me, as I do this, it just seems to kind of make sense to me. This would be an or, because a 10 would make this true, or an 11 would make this true, or a 12 would make this true. And anytime we see an or with probability, what do we do? Or always means that we should add. So this would really be the probability that x equals 10 plus the probability that x equals 11 plus the probability that x equals 12. And we'll usually kind of skip ahead to this step because we kind of know that it's an or. But you should actually be writing this out. You should be writing that these are my 3 probabilities I'm finding. You should be writing the probability that x equals 10 part. Make sure you're showing your work and you're writing enough out that you're being able to stay organized. And for each of these probabilities, you just go back up and look at your chart or your graph if you prefer. So for x equals 10, that is at, well, if I draw it to scale, we are at 3 out of 36. For the 11, we're at 2 out of 36. And the 12 is 1 out of 36. So this would be 6 out of 36. Again, you can simplify your fractions, but if you're going to be doing a lot of problems that all have the same denominator, I just keep it as it is so you can compare them easily. So let's try now the probability that x is less than 5. So what would this be? So you actually write it out. So you say, okay, if we're less than 5, x could be, let's see, can it be 1? No, 1's not an option. So we start at 2. We'll include the 3. We'll include the 4. Should I include the 5? No, because it said just less than 5. And so again, just look up at your chart or your table, and we have a 1 out of 36, a 2 out of 36, or a 3 out of 36. Add those up and you get 6 out of 36 again. Our next one has the probability that x is less than or equal to 2, or x is greater than or equal to 9. So again, just go through and list out everything that applies to this. So x is less than or equal to 2, that would be just x equals 2. Plus, let's see, x is greater than or equal to 9. So we'd have to have a 9. X could also be 10. X could be 11. X could be 12. Now, if I have any of those numbers, does that satisfy x is less than or equal to 2 or x is greater than or equal to 9? Yeah, so those are all the numbers that satisfy that. So the probability that x equals 2, let's see, that is 1 out of 36. For the 9, let's see, we're at 4 out of 36, 3 out of 36, 2 out of 36, 1 out of 36. So 11 out of 36. And it might seem like it does take a while to do these. It does. Everything we do with discrete distributions kind of takes a while because you have to add them all up one by one. Our next one here, do you see this and? This is kind of a deceptive and. Because you might see it, you might want to start multiplying and different things, but this isn't actually the probability of two different events. This is still just one event. We're still only tossing it one time. Okay. And you don't really know if they're independent or dependent and different things like this. Just list out the outcomes. On these types of problems, you just list out the outcomes that actually satisfy that. So for you to be greater than or equal to 3 and less than 6, what outcomes actually satisfy that? What numbers fall into that range? We could have a 3 or a 4 or a 5. So x equals 3, x equals 4, x equals 5. So this would be 2 out of 36 plus 3 out of 36 plus 4 out of 36, which is 9 out of 36. So you're going to be doing lots of problems for this on the entire chapter of Chapter 2 and Chapter 3. And again, every time just list out the x's that apply, find the probabilities from there. And my favorite one, the probability that x equals 13. Okay, what would this be? So we'll wait for someone to give us our answer. Okay, so here in Brigham we have that it's 0 because it's not possible to get 13 when you roll two 6-sided dice. Okay, and so this is impossible. So anytime you get something that is impossible, it would be 0. And similarly, the probability that x equals 6.2, can you get a 6.2? No, so that would just again be 0. So you will have problems as you go through where you just get zeros. You say that's not possible. So we're about to switch gears fairly drastically. So before we switch gears, do you have any questions on what we've done today? Okay, so we had our probability mass function, our PMF, and that described the probability for each x value. Now we have what's called a cumulative distribution function, which we'll do as a CDF. And this is a function that describes cumulative probabilities. Now cumulative means kind of add them all up, right? So if you have this capital F of x, that's what stands for CDF. And it's always equal to the probability that x is less than or equal to some specific value. So instead of x equals 1 or x equals 2, it's now x is less than or equal to 2, or x is less than or equal to 5. So if we have a discrete random variable, we can find the CDF by adding up all of our probabilities that are less than or equal to x. So again, very fancy notation. You'll find in this class, in this textbook, you have always very fancy notation for formulas. So we'll take the sum. But really, all you have to do is you just add up all of the probabilities up to that x value. Now, the interesting thing that they did when they defined this, the person that invented it gets to make the rules, cumulative distribution functions are always defined for all real numbers. Now, what I mean by this is on our last one, what numbers did we actually define the PMF for? We only defined it for the numbers 2 through 12. The CDF, though, we'll define for all numbers. And we'll see what that looks like. Let's see. So here's our PMF again for the number of heads if we toss our fair coin 3 times. Find and graph the CDF. So again, here's our PMF, which we found previously. We could do the table, but I think I'll actually draw the graph first. That's what I was thinking about earlier today when I looked at my notes. So we have an x, and over here we have our capital F of x. My probabilities are eighths, so I'm going to do a scale of 1/8. Let's see, this would be 4/8, 5, 6/8, 7, and 1. For my x's, we had x's, at least that we're interested in, of 0, 1, 2, 3. And I'm going to start here because I want to say, okay, what are my actual numbers we're interested in? 0, 1, 2, and 3. At 0, I had a probability of 1/8. So I'm going to make just a dot here. This isn't done. I'm just starting with some dots. Now, for x equals 1, though, how much probability do we have altogether? So for x equals 1, the cumulative distribution function has all that number and all the numbers less than it. So for a 1, you have to have the 3/8, but you also have to have the 1/8. So how much probability is that total? If you add them together, you're at 4/8. And for the 2, you have to have 3/8 and 3/8 and 1/8 because it's everything less than that. So you'd be at 7/8. And for the 3, you have to have 1/8 and 3/8 and 3/8 and 1/8, which is 1. So those are the actual values that we care about. But instead of defining for all real numbers, and the way you actually do this is you say, okay, so from 0 to 1, at 0, I have a 1/8 probability of getting that. But what is the probability? Let's say we had a 1/2 in here. What's the probability of, say, getting x less than or equal to 1/2? To get x less than or equal to 1/2, that's basically just the probability that x equals 0, which is 1/8. So what should be the value at 1/8? It should be, or at 1/2, it should be 1/8 as well. Or like the probability that x is less than or equal to 0.9, that's really just the probability that x equals 0 because that's the only possible value less than 0.9. So it'd still be 1/8. So you can see that all the way along here, we would have a probability, or a cumulative probability of 1/8. So what you'll do is you'll actually draw in this flat line, okay, until we get to 1. And once we get to the 1, what happens? We're supposed to jump. So what you do when you draw your cumulative distribution functions is you fill in the left endpoint, okay, and then the right endpoint is always empty because at 1, we got more probability. And so we jumped up. But then it would be flat again until we get to 2 when we would jump. And it's flat until we get to 3 when we jump. And so these are always step functions. We mention them occasionally in other math classes, but not very much because we don't really like them because there's not nice formulas for them. So these are step functions where you always include the left endpoint. So when you do the CDF, it will always include the left endpoint. Now it did say define for all real numbers, so I also have to figure out what would it be for numbers bigger than 3. So let's say, what would it be right here at x equals 4? Or the probability that x is less than or equal to 4. Well, for x less than or equal to 4, that would be x equals 1 or, 0 or 0 or 1 or 2 or 3, right? All of those would be less than or equal to 4. So it would just be 1. Or anything greater than 3, the probability would always be 1. So this probability, or this line, would kind of go on forever. So we're going to be 1 forever. And let's see. What if you wanted a probability that x is less than or equal to, let's pick something less than 0, like -1. Is that even possible? Okay, well, my only values are 0, 1, 2, and 3. So can I be less than 0? Can I be less than -1? No. The probability is 0 because you can't be less than or equal to -1. So all of these probabilities over here would be -1. So we have an open circle, and these probabilities are 0 for everything less than it. So that's kind of why our graphs look like this. From now on, you can kind of remember it will always include the left endpoint, and you jump where you actually have probability. So at 0, I had a probability, so I jump. At 1, I have a probability, so I jump. 2, I jump. 3, I jump. And then over here, let's actually now write it out in a table form. So let's do values of x, or in other words, xi. And then over here we'll have our CDF, or f of x. Now these always, I kind of have to stop and think about it quite a bit to write things out like this. So based on my graph, where do I actually start? Okay. So I kind of, sometimes I go through and I write, what are my values, my actual specific x values I'm interested in? I have a 0, a 1, a 2, or a 3. Well, for x less than 0, I just got a value of 0. But for x between 0 and 1, notice 0 is included and 1 is not, I get 1/8. Okay? Because at 0, I have a 1/8 probability. Okay, so at 0, I have a 1/8 probability. At 1, I now have a 3/8 probability, but it is cumulative, so I also have to include anything before that. So I have 1/8 plus 3/8, which is 4/8. At 2, I have a 3/8, but again, you have to include everything less than that. So 1/8 plus 3/8 plus 3/8 equals 7 out of 8. And at 3, well, there's no upper endpoint here, so we'll just say for 3 less than or equal to x, we have a 1/8 and everything down below, so 1/8 plus 3/8 plus 3/8 plus 1/8 equals 1. Okay, and so that's what matches with our actual table here. The fact that it's defined for all real numbers makes it much more difficult to actually think about what to write here, but what you really, again, try to remember is the cumulative distribution function means that probability and everything less than it. So let's try again. Here's just another random PMF. Let's find and graph the actual CDF. So we'll have each x value and each CDF value. In fact, we don't even put xi on it because it's all values of x. Because we're not doing just 0, 1, 2, and 3. We have to do all real numbers. So what I usually do is I write down each of the numbers that I'm actually interested in, and then kind of go through and fill in the rest. So I'll have to start with x less than my first number, and then the next one will be x between -3 and 0. But you'll always include the left endpoint. So it'll be a less than or equal to, but the next one is just a less than. So then x is between 0 and 2. X is between 2 and 5. X is between 5 and 7. X is between 7 and, well, I guess infinity, so we don't actually have to write that. So again, just remember, you have to have all real numbers, but it's always a less than or equal to first because you include your left endpoint. So your first one, so less than your first number will always be 0 because you don't have any probability yet. And then you just go through and put in each probability. So my next one, at 3, I get a probability of 0.1. And then at 0, what is your probability? You have 0.25, but also put everything up above. So 0.25 plus 0.1 is 0.35. And at 2, you have a 0.15 and a 0.25 and a 0.1. So 0.15 plus 0.25 plus 0.1 is 0.5. And at 5, you now add in a 0.2. So 0.15, 0.25, 0.1, 0.2, oh, 1, 5, sorry. Oh, let's see. That was just 0.1. 0.7, and your last one will always be a 1, okay, because 0.7 plus 0.3 is 1. So you should always start at 0. You should always end at 1. That's how you know you did it correctly, or at least one part of it correctly. So you put your x values, and over here we'll do our f of x. On your x-axis, you'll put, well, your x values, and your y-axis is f of x. 3, 4. I'm going to go with a 0.5 or 0.1 scale. So remember, we always include our left endpoints. So for anything up to -3, we're just at 0. So starting over here, coming up to -3, we're just at 0. But at -3, we get a jump to 0.1. So include the left endpoint, but not the right, and then we go to 0. And at 0, we get a jump up to 0.35. So 0, we're at 0.35. Include the left, but not the right, and we get to go to 2. Sorry. And at 2, we jump up to 0.5 and go over. Don't include the right endpoint. And at 5, we jump up to 0.7. And at 7, we jump up to 1 and stay there forever. Okay, so any thoughts on that one? And again, don't worry, to me, these are always, you have to think about it, very hard. It takes a little bit of practice. So we learned how to go from a PMF to a CDF. What if you want to go the other way? So now in this next one, we have values of x written down, and I told you what the CDF is. Now I want you to tell me what the actual PMF is. This one to me is actually pretty easy because I can give you a specific thing to look for. So number 1, you're going to try and figure out where did f of x jump. Okay, and then 2, you're going to ask how much did it jump by. So we have a jump right here. So where is that jump at? That jump is at -3. So the probability that x equals -3, that's where my first jump was. And how much was that jump? How much did it go up? So looking up here at -3, I'm now at 0.1. I was at 0, so I went up 0.1. Or looking at my graph, I went up 0.1. So it jumped by 0.1, so that's the probability at x equals -3. The next place it jumps is at x equals 0, so the probability that x equals 0, so come back up. I was at 0.1 and then I jumped up to 0.35. So the difference there is 0.25. So this jump is 0.25. So the actual probability at x equals 0 is 0.25. So at 2, we have another jump. And it looks like we went from 0.35 to 0.5. That's a 0.15 difference. So the probability that x equals 2 is 0.5 minus 0.35, or 0.15. And the probability that x equals 3, not 3, let's see, my next jump is at 5. So probability that x equals 5. Let's see, we were at 0.5 and we went to 0.7, so that's a 0.2 jump. And my last one is at 7. I jumped all the way up to 1, or a 0.3 jump. So probability that x equals 7 would be equal to 1 minus the 0.7, or 0.3. So this was easier for me because I had my graph. I could kind of look at my graph and see how much did it jump. But really, you also just come back over here and you say, where are your jumps? So from here, I went from 1, or 0.7 to 1, so that was a jump of 0.3, and it happened at 7. Or right here, I went from 0.35 to 5, that's a 0.15, and it happened at 2, etc. So it's really just where did it jump and how much did it jump by. So then, for my actual PMF over here, you have each x value and each probability value. We were at -3, 0, 2, 5, and 7. And those probabilities were 0.1, 0.25, 0.15, .2, and 0.3. So that's how you actually reconstruct it or go back to a PMF. Now we did that just kind of by logic. Our textbook does have an actual formula, which I don't really like. I'd rather just remember the way I did it up here. So the probability that x is equal to some specific value is going to be the CDF at x minus this, notice this capital F of x with the little negative up there. If you think back to calculus, that kind of seems like, or it might seem like the notation they use for limits. So this actually refers to the limit of f of x as we approach x from the left. And so what that means is, as you're looking up at this graph, f of x here is 0.35, but as you came from the left, my actual limit was right here, so my actual limit was 0.1. Now to me, thinking about that is a lot harder than just saying it's the probability that x equals some specific value is the CDF at that value minus the CDF at the last x value. That's a lot easier for me to keep track of. So if I wanted, say, the probability that x equals 5, I'd come back up to my chart and I say, okay, what is it at 5? At 5, I'm at 0.7 minus the last one, that's 0.2. That's easier for me. So it's a little bit early, but I think this is probably time to take our break. So do a 10-minute break, and we'll come back and start in the next section.